Welcome to the HPC Best Practices webinar series. This series is brought to you by the IDEAS Productivity Project, which is part of the exascale computing project of the US Department of Energy. And this series is a collaboration involving the computing facilities at the Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. I'm Osni Marquez from Lawrence Berkeley, and will be the host for today's webinar, Growing preCICE from an as-is coupling library to a sustainable batteries included ecosystem. And the webinar will be presented by Gerasimus Churdakis. Gerasimus is a doctoral candidate at the Technical University of Munich, where he takes the leading role in organizing the development operations of the flash of the preCICE ecosystem. This includes adapters for various solvers, tutorial cases, documentation, website and testing, and also shaping these components for the preCICE community to grow upon. He is also researching methods for geometric multi-scale coupling and enjoys teaching topics related to research software engineering. With that, Erasmus, take control.
Thank you very much, Osni. Let me share my screen. All right, now I think you can see my screen. And yes, I would like today to talk about an ecosystem. And I'm talking about an ecosystem because a few years back, when I and a few colleagues of mine started our PhDs, we got a very nice library in our hands, the core of our ecosystem today. And we built upon this. Others made the core even stronger. And I worked on adding more flesh to the ecosystem. And let's have a look at what is it that we are talking about, first of all. So the motivation for a coupling library, or at least for preCICE, is that we want to do partitioned multiphysics simulations. A very classical example is fluid structure interaction. And in this picture, you see a famous benchmark by Turek and Kron, where you have a channel flow. So we have a CFD code, and there is an obstacle in the middle. You may know this picture where the flow around the cylinder creates this Karman vortex thread. And now imagine that downstream, you also fix a flexible flap, which will then start moving based on these oscillations. Instead of solving everything in one code, we actually want to reuse the expertise of a structure solver, which we want to plug in to our flow simulation. And we can do this with preCICE. One alternative application, also very common, is conjugate heat transfer. Here you see a cell and tubes heat exchanger where a cold fluid and the hot fluid are exchanging heat. Especially in this scenario, and one nice feature of preCICE is that here you see more than two coupling participants. We have two fluids separated by a solid. Okay, but let's now dive a bit deeper and try to understand what is this library. Imagine that on the one side you have flow code, let's say OpenFOAM, and on the other side you have a structure code, let's say Calculix is a famous example, or some other codes that I will explain in a moment. As I said, we want to take our flow simulation and plug into it a structure simulation. We can do that by using the preCICE library in both the solvers that we are using. As you see, both solvers are published standard solvers, experts on their fields, and you only need to add this preCICE library to make them talk. How do you do that? You essentially need to call the library, and these additional lines of code that you need to call the library, we call an adapter. In case of OpenFOAM, this is a nice plugin. In other codes, this may be some additional code changes directly in the code or in any other interface it may provide. The library itself takes care of data mapping between the meshes of the two solvers, which can follow completely different discretizations. In this case, we have a finite volume mesh, in this case, a finite element mesh. All that preCICE knows is a cloud of points and potentially how they are connected. The library also takes care that there is efficient communication. So this can run efficiently from a laptop to a supercomputer with MPI. And in addition, this library will make sure that we iterate efficiently the two sides of the simulation until we converge to the same truth on the interface. This is something we call implicit coupling. But this is a picture. How does it look in code? Now, in every code, in every simulation code, you usually have a transient loop. You have a solution step where you solve for your current time step size, and then you need to call preCICE. You need to inform preCICE about the new values you got on the boundary. So you fill a buffer, you write data, in this case, force, if you want to do a fluid structure interaction simulation. And then you ask preCICE to do its magic. You ask it to perform data mapping, communication, and a coupling step. And it will do that for the same time step size. In the end, it will give us a new allowed time step size for the next iteration, because we may need to actually synchronize again. Then, in the end, preCICE will also give us new boundary values that we can read in our code. In this case, we want to read displacements. The actual code is a bit more complicated, but it boils down to this simple example. Now, if you are actually an applications engineer, if you come from mechanical engineering and you want to do a multi-physics simulation and not to write code yourself, you may find that using a library may be a bit complicated for you. You may want something that you can just start running. And this is where the whole story begins. So by including ready-to-use adapters and examples for many of these famous solvers, we have essentially created an ecosystem that people can just take components off the shelf and in many cases run simulations. And that's what I want to talk to you about today. If you have my slides, which you can also find the link for in the chat, the slides contain links. So you may see here already OpenFOAM. This is a very famous code for which Tomislav Marik also gave a talk, actually 2 talks about in this same webinar series. And you may also see DL2, for which also Wolfgang Bangert also gave a talk recently. Now, if you still are a developer, you have your own code and you want to use the library as always, this is something you can do. preCICE is a C++ library, C++14 in particular, but we now have language bindings for essentially any language you may need in scientific computing. If not, please let us know, we will add it. In the process of building an ecosystem, it was very important to also build a nice website and documentation. I would like to walk you through into that and show you some important components. This is the homepage. You can find the code on GitHub. You can download our latest release, or you can get started. You can find different examples that may look closer to your application and replace one of the solvers with the one you like. But the first example you may want to run is this quick start. This page is written with the perspective of a new user that has their own laptop where it's running Ubuntu and they can actually install some things. Most of our users want to use OpenFOAM. So we have here a simple example where we have a channel flow And instead of the flexible flap that I showed you in the beginning, we have something close enough that can be simulated with a very simple toy solver written in C++. And this is just a rigid body motion solver. Now, you can follow all the steps and install preCICE, OpenFOAM, the OpenFOAM adapter, get the examples and build this code. But you don't need to do all this, and you don't need to do it today. I will show you a demo for which I will use a demo virtual machine. This is a Vagrant box, which is actually a bit more than a virtual machine. And I will be happy to answer questions about this later. And essentially, this is something you can run on Linux, Windows, Mac OS, whatever, and it will start a full Linux environment on your desktop. This is something that you can also SSH to, but let's here use the environment. You see here, I have loaded this virtual machine. I can move windows around. And this is the quick start tutorial. You see here that we have two cases. We have this fluid OpenFOAM. This is the flow case. And we also have the solid simulation, the structure with this C++ code. Let's go into this fluid code, and actually let's just show the files it contains. If you're familiar with OpenFOAM, this will look very familiar. You have a pimple foam setup, and you have here just an additional configuration file, preCICE, which essentially tells us which patches of OpenFOAM to couple, and that we want to write forces and read displacements. On the solid side, this looks relatively similar. We just have a C++ code. And you see here that we also have a preCICE configuration file. This configures at runtime what kind of data we're coupling, who is participating in the simulation, what kind of mapping we have, who executes it, what kind of coupling we have, if it's explicit, implicit, what kind of acceleration methods we have, for example, quasi-Newton, and so on. Everything is configured at runtime. And the interface of the library remains the same. It's relatively high level in the sense that you don't need to change it for every feature. Other than that, you just see some convenience scripts. Now, how would we start? In this case, we have two participants. So I'm going to split my terminal in two. I'm using here Terminator and terminal emulator that can do that. Okay, let's go to Fluid OpenFOAM. And these are the files I have. And let's go here to solid CPP. And these are the files that I have. Instead of starting OpenFOAM manually, like making the mesh and starting the code, I have just made this run script to not have to type everything, but this is just starting an OpenFOAM simulation. What you see here is that OpenFOAM has started, and it has loaded preCICE version 2.3. This is not the latest, but this is also a great question for the end on why this is not the latest at the moment in this virtual machine. And it is looking for a configuration file in the parent directory. So this needs to be at a common directory, essentially, or at least by common practice. And it tells us that it is participant fluid, and it is waiting for the other side to appear. We may have not even compiled or decided what the other solver is going to be. In this case, we have decided it's our C++ solid solver. And I'm going to also start this. And you see here what is happening is that while the one solver is simulating, the other is waiting, and then the other one is simulating, and so on. This is a serial implicit coupling scheme. It is also iterating again and again. Now, to save some time, even though this should not take long, I'm going to cancel this and directly show you the results. I have loaded here in ParaView the case. we have here this flow simulation. And here we have, where the gap is, we have our structure simulation. We are doing here fluid structure interaction with a technique called arbitrary Lagrangian Eulerian, which essentially means that we are not going to change the mesh. We are only going to stretch and squeeze the cells of the mesh. We have an additional field called displacement. And if we visualize here the velocity, you see here that the flow is developing until some oscillations start appearing. And after the oscillations start appearing, some force is exerted on the fluid, and this rod moves up, and eventually it will start moving down. And so on. So this is how we do fluid structure interaction simulations. And the beauty of it is that we can actually exchange the fluid and the structure solver with anything else we may want without the one solver knowing anything about the other solver, apart from what kind of fields they are exchanging. All right. So I'm going to stop this now and return on my slides. This is the demo that I showed you, and it would make me very happy if you would also run it yourself and send me an email with questions or some screenshot with your results. I would still like to show you a few things on the website because I have told you what this is. I think I've caught your attention in its potential, but I now want to show you that it can do more than fluid structure interaction. And I also want to support my claim that we have actually built something that people are using nowadays. First of all, if you want to couple your code, you can find already here some documentation that goes step by step into the code that I told you. Many people have followed this procedure for their codes, or they have used some of our solvers, some of our adapters to couple existing solvers. You can find here a dedicated section on our website regarding the community. And you see here a relatively short list of community stories compared to how many users we actually know. So if you have used preCICE in the past, please send us a short text. We will be very happy to advertise your work here. Here you see, for example, again, fluid structure interaction with rotating bodies. This is a cycloidal rotor or fluid structure interaction. But then you see a simulation that is actually coupling a muscle system where you have the muscle tenons and you also have the muscle belly, and you're coupling it with an electrophysiological model. You also see here some acoustics. You see some coupling of subsurface flow solver. This is pFlowtron with a code that tries to optimize where you put heat pumps in the city of Munich. People have also used this for essentially for fracking simulations and other porous media. While we have also used it, and we try to extend preCICE to be able to couple solvers of different dimensions. Most of the users are from the industry, from academia, but we also have some users from the industry. And here you see one such contribution where they integrated preCICE into a complete graphical interface with other solvers. And let me now return to the homepage, where at the bottom you can find a few more hints on who is currently using preCICE. We estimate the current number to around maybe 100 groups or more. Most of them are universities, mostly in Germany and Europe. We know of some institutes in the US. And yeah, there are also a couple of industrial users. Now, I hope I've got your attention to the fact that, yes, this is something that people are using. This is not just a code that is used inside one research group. And yeah, this is something that we actually really want. Now, since many people have used preCICE, you may think that we had already many collaborations. This is partially true because we know of many users that actually, yeah, just appeared through a publication or a poster in a conference, and apparently they were using preCICE without us knowing anything about it. So I would claim here that you don't need to talk to us to successfully use preCICE. And if you think of it, this is actually an achievement. Often you go to conferences and you see very nice results, but then people rarely talk about the software itself. And if you try to reproduce the results, you contact the author and they have to sit with you through some sessions on actually installing the software and helping you actually use it then maybe for your application. We try to make this as open as possible. And we try to enrich our documentation as much as possible because this is also what we are using. However, it's not only the documentation. Sometimes you want to contact us. And we have also built a nice set of community channels. So I would also claim that if you want, you can actually reach us very easily. You don't need to find out who is actually developing and send emails to the developers, but you can, for example, write on our forum. And something that made us very, very happy at some point was a user writing on our forum that after the amount of support I have received from this community, I'm switching to open source for every one of my needs. And essentially this sends a message that developing open source software and making it nice not only makes the software itself nice, but also improves the reputation of open source software as a whole. And this is now a good time to get some questions if there are any.
Actually, hi, Erasmus. There is one here. Actually, the participants typing. Let's see if I can. Real time. So let's see.
Okay, I can read the question.
It. Good. Yes.
Yeah. So the question is, can you compare preCICE to previous efforts in coupling libraries, such as Fraunhofer's MPCCI or the coupling libraries used in the climate community? That's a very good question. So MPCCI predates preCICE, this is clear. And as far as I know, it's a proprietary code. It's not developed in the open. Even though some components, for example, the OpenFOAM adapter is released as GPL software. So preCICE does not use any central component. There is no server or so. They also have, I think, a wide ecosystem of supported solvers. Yeah, the main advantages of preCICE, I think, is really the open ecosystem, the documentation, the community, as well as the advanced algorithms that we offer nowadays, such as the quasi-Newton acceleration, the RBF mapping, and many features that we are developing now. And you can even see our roadmap in the open. So we develop everything really publicly on GitHub, and we even document what is going to come next. If I could compare it to coupling libraries used in the climate community, this is also a very good question because people traditionally thought that preCICE was only for fluid structure interaction, but this is not the case. Essentially, you can couple any code that you can bring on a mesh. You can get points from the one solver, and you want to bring the information from these points to some points of another solver. So you can also use it to breed macro and micro scales, for example, even though there are tools that more traditionally follow that approach. But preCICE is much more than fluid structure interaction and can be applied in other applications. All right, but since there are no questions now, I see someone typing, we can take up next. I would have a question that is, okay, nice talking about all these things and nice developing documentation and so on, but why are you even bothering? Why are you doing all this effort? And yes, it's a lot of effort, and we are usually not paid exactly to develop preCICE. We are paid to do some other projects, and most of us are doing our PhDs. So why do we actually need users? Well, in our research, we are mostly dealing with methods and software, but we do need users that will actually apply these methods and software to the shiny applications. And only then, first of all, we know that things are working, and only then we give value to our research. Through this process, collaboration starts. Through this process, we can get more funding to keep developing our methods and software. All right, so we started from a library that was already very good, very strong. And we now have an even stronger library that is used by many people. And alongside that, we have a rich ecosystem of supported solvers, as well as the documentation and everything else. We have done some things that we realized that they were not the best decisions, and we have corrected them later. And we have learned a lot in the process on what was effective and what not. So I would like here to talk about some lessons learned. First of all, some technical aspects. As I said, preCICE is a library, meaning that you don't have to adapt your code to fit some coupling framework, but you have your code and you just call a few additional lines of code, similar to how you would call MPI or you would call a plotting library. It is much easier to adopt a library in your code. Then, in the complete development, we have separated the concerns, meaning that the library is developed in a separate repository than all the adapters and all the language bindings and so on. This has the great advantage that you can give projects to students, for example. They can work on it on their own time. There is no risk involved. And only when something is ready, you can integrate it. You don't need to have a branch dangling somewhere in the repository. You just have a completely different project that can be plugged in at runtime. Something we have improved is that we have made our dependencies a lot fewer, and we try to stick to as common dependencies as possible. We don't want anything exotic. Right now, we have some build time dependencies such as eigen. This is very common. And we have a few dependencies also at link time. This is also NPI, PETSI, and so on. But these are also optional dependencies. You can switch them off because they only concern specific features. And when a user just wants to do a simple simulation on a laptop, they don't need that. They don't need to try to install all these additional packages. Then for our common user that it's often a PhD student that just started their PhD, they don't want to build code from scratch. What they actually need is to apply it in an application. So we try to make every step easier. For example, we give packages for common platforms, for example, for Ubuntu. And you see, we have all this complex setup of building a multi-physics simulation. We have so many components. So reducing the effort just a bit in every component really pays off. in the user experience. Then on the technical side, we try to adhere to many guidelines of standard practices. You know, of course, here in this community, the Extreme Scale Development Toolkit. preCICE is now a full member of that. And you can also find out the policies that we have implemented. Then there is the open source security foundation best practices. This concerns not so much scientific projects, but it also applies to us. And it has different levels. For example, you can get a basic level certificate just by essentially making up your mind on, do I have version control? Is everything developed in public? Can people just follow some documentation to install the software? So this is really good if you're just starting. And of course, we have several linters and code quality checkers that can tell us, for example, if we have parts of untested code. Another aspect is the documentation. And something that did not work well for us in the past was that we had documentation scattered in different resources. We had a very basic website, which was essentially a flyer, and it had little value after the first time you read it. We had a GitHub wiki for preCICE itself, and then we had different GitHub wikis for the different adapters. And finally, we had the developers' documentation on Doxygen. And often we had links from the one to the other side. This is a very common situation, but this was very distracting. So what we did now was that we made a nice website. And the website itself is in a repository that does not actually contain all the content. A lot of the content is sourced from different repositories, because this way you can actually have the content next to the code. You can have the documentation next to the code. A big advantage of that is that you can update the documentation in the same pull request as your code. At the same time, you see our tutorials, for example, are stored in another repository. And what you see on the website is essentially a rendering of the README file of the tutorials, which means that if you have already cloned the repository of the tutorials, you know how to run them, even if you are on a train without internet connection. Another lesson learned was that people sometimes find issues and want to fix them. And you really want to catch these motivated users. For this reason, we have added an Edit Me button on the top of every page. And you can click on that. And this will take you to GitHub. This is the only complication, that you need to have a GitHub account. And then you can edit the file, which is Markdown, so it's very easy. And you can automatically start a pull request, which will be reviewed by one of us. So there is no stress that you're doing something wrong. Someone will actually check it. How do we do all this? Well, we sat down one day or many days and discussed the structure and how to do it and so on. We have now a website based on GitHub Pages. So that's a Jekyll server. I think also in the Better Scientific Software, you're running such a system. And it just has some style sheet on top based on Bootstrap. So there is a bit of JavaScript there. While we do maintain the content ourselves, we got some help by hiring someone to build the general style and structure. Then some other things that came with this was that we have a very nice search functionality. For that, we use Algolia, which is also free for open source projects. We have the possibility to export a complete PDF of the website. This is great if you want to archive the software, or if you want to really make something citable for the future, for a specific version. And for that, we use a tool called Prince. And we even have some basic user analytics, which are actually privacy respecting. So we don't need to adhere to any special cookies law, because this is already taken care of. Then another aspect on the documentation is more philosophical. So imagine that someone asks you something that is currently not in the documentation. Instead of actually writing a long email explaining the issue, you can instead add it first to the documentation and send them a link saying, okay, thank you very much for finding this issue. And yes, and then you can just send this documentation. I see in the chat that someone asks if I'm frozen, so please confirm that everything is all right.
It looks good here.
Okay, thank you. And I really liked the other day looking for the status of my flight at Lufthansa when I read the note on their flight tracker that said, please note, all the flight information displayed is up to date. Our service centers also obtain their information from this flight status feature. And this is something that is a very important strategy, because only in this way you make sure that the documentation is up to date, only if users and developers access the same resources. So you update it together with the code, you render it on the website, and everybody is looking at the website. Another aspect that we worked a lot lately was building a community and building communication channels. We started with a mailing list, which I think is very common in especially many older projects. But yeah, let's face it, mailing lists do not scale, and many of the new users do not really feel that the mailing list is for them. They don't want to bother too many people that will receive this email, for example. This is also a filter, but I would argue that you want even the most hesitant users to ask questions, because only in this way you discover more issues. We also have a chat room. This is on Gitter, but this is a platform that is slowly dying and potentially being replaced by Matrix. And many of you may have Slack. The problem there is that you cannot easily search in the past, and the discussions are not really in a threaded view always. I know there are implementations that do this better, but still what it is actually much better is a forum. And then you can ask, should I create a forum on, for example, CFD Online? This is a popular platform in our community. Or should we create something on ourselves? For us, because we wanted more control and we wanted something more modern, we decided to offer our own forum. And we use Discourse for that, which is an open source tool. And it is also offering free hosting for open source software projects. And it's really great. It has threaded view, it has a great search. So if you start typing a question that has been asked in the past, you will get suggestions. You can organize your topics into like what solvers are used, what category they are in, and so on. And we also use it to post some news, so some blog-like functionality, to write common questions and answers, and even to network people during conferences and workshops. Let me quickly show you how this looks like. This is the thread that I mentioned before. You can even interact, you can mark what is the solution to your question, and so on. All right. Then this is the way the community communicates online, but of course we also have offline communication. The best way to meet us is to come to one of our workshops that we are organizing every February. And there we don't only have talks by users and developers, we also offer training. We also ask the community for feedback. We have a World Cafe style discussion where people discuss specific topics on different tables and shuffle around. And we also sit together with users and discuss their problems individually. Finally, let's face it, if you need users for your project, it is essential that you try to get them. So also talk about the software in conferences and yeah, talk about the software. Another thing that we learned recently was that, first of all, people don't like upgrading so often. They want to focus on their application. But at the same time, we are developing new features that need to find their users. So we decided to not do breaking releases. So we went from preCICE version 1 to version 0.2 after maybe 3 or 4 years. Our goal right now is 2 to 3 years minimum. And at the same time, we want to release new features often, but not too often. We had a release cycle of 3 months. This consumed a lot of work from our side. People were not really upgrading, and we decided to just do it every 6 months. We now actually have every 6 months a release of the library, and after 3 months, a release of other components. So we have this flip-flop strategy. The downstream components, however, can actually be released at any time. There is no restriction there, but if we have breaking releases or new features, we try to synchronize them. And we also built a complete distribution of the ecosystem. That means essentially which versions of each component work together. And we make them in a citable format. So we put them on a Dataverse instance, something like Zenodo. And we try to distribute 1 or 2 of these per year. This is the reason that in the virtual machine I showed you, the preCICE I used was not the latest version. Okay, something that we are still learning now is how to publish about the software. We had our first reference article that most of the publications using preCICE nowadays cite. This was in 2016. However, many of the features described there are not exactly the same anymore. New features have added, some things have changed, more applications have been added. And more importantly, since we are in academia, most of the developers now have changed, and there is essentially no citations to the people that are actually involved with software in the past years. So we now release the second version 2 paper. We try to also release reference articles for adapters, as well as for specific features. For example, you can find papers discussing only the performance of the library. And we also have the distribution that I just talked about. I would now like to slowly start fading out. First of all, by saying that you are very warmly invited to our next workshop. This will be in Munich. The dates are fixed. We know that in the winter, there may be some restrictions due to Corona, but we are anyway always ready to switch to an online format. We did it like this twice. You see here a screenshot of the Big Blue Button instance we used this year. And we will announce more details in fall when it will be a bit clearer where the situation is heading to. Well, I know this is a lie, but we can only hope. Okay, so finally, a challenge is how to get sustainable funding. We have not learned about this. We are trying to find solutions. We have a research-driven project. We develop new methods, and they are for a very niche topic. So academic funding will always be important. Maybe there are not even enough industrial users to support this just by industrial funding. And at the same time, you cannot just offer support. You really need to develop the methods further. So one thing we have tried and works nicely is that we write research proposals together with users. We organize workshops, and this can give us a little bit of money that is actually more flexible. So we can also print stickers or things like that. And of course, we can work on the website. And the solution that we now have to deal with the growing requests for collaboration and support is that we have a paid support program, meaning that we still support everyone in the same way on the public forum. But if you actually need more reliable day-to-day support, you can apply, similarly to a software license, you can apply for a support license in your academic proposal. And this way you ensure that the software that you rely upon will still exist in a few years, and that you will have support that can actually make your project more successful. A few things that I have not discussed today is anything about the features, the performance, and so on. I've not discussed how we do testing and continuous integration. We wrote a very nice first blog post about that, and there is another one coming about our system tests. I've not discussed how we collaborate and organize our projects, and how we do outreach. However, hint here, we are very happy to talk about this in further talks. So if at some point you're looking for speakers, please contact us again. What I discussed today in a large extent is discussed also in our version 2 reference paper. We were very happy to be able to publish to the Open Research Europe. This is an open access journal funded by the European Commission. Also, the peer review is completely in the open, and now the first version has been approved. We will push a few improvements in the next few weeks or months. And yeah, Osni in the beginning mentioned that I'm involved in the development, but many people are involved in the development. Here with us today is also Frederic Simonis from the same group, also a colleague. You also see Boris Martin, who is a working student with us in Stuttgart. And other people that you may have met are Benjamin Neckermann, Miriam Schulte, both professors in Stuttgart, as well as Ishan Desai, David Schneider, Carl Davies, Benjamin Rodenberg, and Kurt Sackfield. In the center of all this, you see a growing community. I would like to thank very much the funding bodies that have supported preCICE over the years. This is mostly German and local or European funding bodies. And I would like once again to refer to other talks in the same webinar series that you may actually find very interesting if you found any of the topics that I talked today interesting. With this, thank you very much. This is where you can find the slides, give me some feedback directly, and give some feedback to the workshop, to the webinar organizers. And this is again a summary of what I have discussed. Please always think of the user. It may be highly beneficial, but this usually needs a few years to show results. Thank you very much.
Thank you, Gerasimus. There are a couple of questions for you there in the Q&A, if you can see them.
Yes. So a second question by Alfred Tang is, the speaker makes it sound like preCICE is plug and play. Yes, I'm still not clear what it is. Is preCICE one single package or a collection of adapters for various libraries? Does it need to be compiled with all the libraries in my code? Do I need to modify my code to use preCICE? Many questions here, and I completely understand the question. With this, maybe let's go back to the beginning. So you don't need, it is not a single package with everything. You can use nothing You can use specific packages of it, but what you will always be using is this green box, the library. And you can use this to couple only your in-house codes, for example. You don't need to use any of this. In some cases, for example, in OpenFOAM, it is really plug and play, because even the lines that you would need to add to your code to communicate with the library, to use the library, are encapsulated inside a plugin interface, an OpenFOAM function object. This really means that you do not need to recompile OpenFOAM in any way. You only need to load this adapter at runtime, which is another small library that you need to compile. Then, is it a collection of adapters for various libraries? It is, in the sense that this is the preCICE ecosystem. So it is the library plus everything else that we have today that we can just cherry pick and couple existing solvers. Do I need to modify my code to use preCICE? Yes, you need to modify it in this way. You need to add 10, 20, 30 lines of code, depending on the language and what exactly you need to couple, but it is really in this range. And the most important is to know your code, not to know preCICE. It is really easy to just add additional lines of code. You don't need to change your data structures. You don't need to change how you call your solver. You just call the solver as you always would. And it is like calling an additional plotting library. Let's say you call VDK to write VDK files. I hope that this answers the question. And then there was a comment referring to the paper.
Yes, I added that one, the comment. So the question was about, it's a follow-on to the first question. It's related to libraries for climate applications.
Did you add something?
No, it's the second question. This was a follow. The participant.
Okay, right. I missed that. Yes. Follow up on the question about the libraries used in the climate community. In climate coupling libraries, there's always a balance that has to be struck between interpolation accuracy and conservation properties, important for long-running simulations. How are you dealing, if you are, with this? I'm not really familiar with climate simulations, so I hope I understand correctly. For long-running simulations probably means that you accumulate some numerical error. What we do, first of all, for interpolation is that we have different methods that are as simple as just picking your nearest neighbor on the other mesh, which is very fast, but yeah, very inaccurate. Or you can actually build an interpolar based on radial basis functions on the other side. And for that, you can say, I want to take the complete mesh into account, or I want to only focus on some region to save time. And this way you can really have a very accurate mapping between the meshes. Something that I think is implied here is really the accuracy of the coupling itself. That is something you can actually really configure. We have this implicit coupling algorithms that iterate, and they also can reduce their iterations, learning from the past. This is what the quasi-Newton method does. And there you can really set the thresholds you want for convergence. You can say, I want everything that I'm exchanging to have an absolute convergence measure of, I don't know, machine precision, which is something that probably would be quite difficult. But there are methods to really achieve higher accuracy. But everything is configurable. So this is in the end up to the user. There is another question at the same time, and I hope I can answer many still. Do the coupled codes run on the same threads while one is waiting for the other, or do I need to allocate more cores while submitting a job? For example, 40 cores for CFD and 10 for FEM, meaning 50 cores in total. Everything is completely MPI parallel. We start in two separated MPI communicators, and every solver can have whatever parallelism it wants inside. Meaning that, yes, if you want to have 40 cores for your flow solver, that is usually the expensive one, and 10 for your structure solver, then yes, you should have 50 cores in total if you want to make sure that every time one core is only running one process. Something that I need to mention here is that in the demo, I showed you a serial or staggered scheme where the one code was waiting for the other, but preCICE also supports parallel schemes in a Jacobi style way, meaning that you can really utilize the full system without having parts of it idling. And that means that the FEM could not use a subset of the CFD cores. I think that if you configure it in a serial way, you could also allow the FEM to use a subset of the CFD cores. But again, what you probably really want to do is to have a parallel coupling where you can utilize your full system. But you have the option to do both.
Any further questions for Gerasimus? We have, I think, a few minutes left here. So if you would like to,
I see one question or clarification in the chat that was conservation properties are on integrated quantities such as opposed to pointwise ones. Yes, we also have interpolation mapping methods that distinguish between mapping, for example, a temperature or a force that really needs to be integrated. I'm sorry, Osni.
No problem. So, you know, I invite people to unmute and ask directly to Gerasimus if there is any other question from the audience. If not, thank you very much for joining us. And for those of us joining from Europe, have a good evening. Thank you very much, Gerasimus.
Thank you very much, Osni, and have a great day.